kids, Miss Kulkarni here. In this video, we will continue with nuclear reactions. In order to write a balanced nuclear reactions, we must remember how to represent a nuclear symbol. O is the symbol for oxygen. 16 and 8 are the atomic mass number and atomic number respectively. If this oxygen has a charge, we represent that as 2 negative on the right hand top side. And suppose if it's the element with maybe 2 atoms like O2, we write that on the right side bottom. One more thing to remember, in nuclear reactions, we should keep an eye on mass number and atomic number for both reactants and products, because the sum total of mass numbers on the reactant side must be equal to product side, and same goes with the atomic number. Let's practice some nuclear reactions now. Alright, so what we got here? We need to get polonium 214. That means that is the mass number. By looking at the periodic table, we can also find out the atomic number, which is 84, and the element goes through alpha decay. Alpha particles are represented as helium nucleus, so it will be He 4 and 2, where 4 is the atomic mass number and 2 is the atomic number. And the element which we are going to get, let's say if we represent that by X, we can find out atomic mass number and atomic number for this new element, because the total of 4 and the atomic mass number which is going to be here should be 214. So very clearly that must be 210. And 2 plus that number should give me 84 as the answer. So I should have 82 as the atomic number. And now we can identify this element, because if we know the atomic number, we can predict what element we got. And for number 82, the element is lead Pb. So in fact, we got lead in this reaction as a product. Okay, let's work on the second one. We need to get bismuth. 210 is the atomic mass number for bismuth, and the atomic number for bismuth is 83. Is going through the beta decay. Beta particles are just like electrons, so it's 0 and negative 1 over here. And now if the element is X, how can you predict the mass? The mass should be 210, because that plus 0 is 210. And look at the atomic number. We must have here 84 to give 84 minus 1 equals 83. And which element is that with the atomic number 84? That is polonium. So we ended up getting polonium in this reaction. Let's move on to the next one. That's arsenic, As70. The atomic number for arsenic is 33. And then that is giving a positron. A positron is something similar to electron, except we put here positive 1. And the new element which you are going to get will be 70. And over here, it must be 32 to give the total 32 plus 1 equals 33. So which element that could be? In periodic table, we find germanium with the atomic number 32. Moving on to next one. This is vanadium 70. The atomic number for that is 23. And then that is actually going through electron capture. So that means electron must be a reactant. So let's write down that on the reactant side. And that is going to give a product. So when we add the atomic masses, that's 70. When we add the atomic numbers, that comes 22. So that corresponds to the element titanium with atomic number 22. Let's work on some more nuclear reactions. Only difference is Partial reactions are given here, and our job is actually to find out which particle is decaying or it is getting captured. Look at the first one. We got nitrogen 13 and 7 as the mass number and atomic number, and the resultant product is carbon with 13 and 6 as the mass number and atomic number. So that means the particle which is decaying should have 0 as the mass number, and we should have over here positive 1. Which particle could be that? That must be a positron. So reaction 1 is positron decaying. Let's look at the second equation now. Second equation is 37 and 18. Let's compare the mass numbers. They are exactly same. So for the particle it must be 0. The atomic number is 18 and 17 on the product side. That means over here it must be negative 1. What could be the particle? That must be an electron. And this is on the left side of the arrow. That means it is on the reactant side. That will be called as capture. So it is electron or beta capture. Let's work on the remaining problems now. There you go. For reaction number 3, we end up getting electron decay. It can be also called as beta decay. And for reaction 4, when we balance the atomic mass number and atomic number, we end up getting helium nucleus, which is nothing but alpha decay. Now, how quickly a radioactive substance will decay? It depends upon the half-life of the substance. And half-life is nothing but the time it takes for 1/2 of the original substance to decay and form the new element. Now, different atoms, different isotopes, they all have different half-lives. The longer the half-life, that means the isotope is more stable. Now, whenever there is one half-life over, half of the substance remain. When there are 2 half-lives, half of half or 1/4 remains. If it's 3 half-lives, it will be 1/8 of the substance remains unchanged. This graph over here will give us some idea about half-life. This is the beginning sample. After first half-life, 50% or half of it is gone and half is remaining. After second half-life, it's half of the previous one or 1/4 of the original is remaining, and so on. So let's solve these problems about half-life. The first one is phosphorus with the half-life of 14 days, and we are starting with 100 grams of sample. Our job is to find out how much sample will remain after 42 days. First of all, let's find out how many half-lives will be 42 days. That will be 42 divided by 14, and that is 3 half-lives. So we can easily find out how much was it before. So let's say at time 0, how much amount we had before anything was decaying. We started with 100 grams. Then comes the first half-life, which is 14 days. And how much will be remaining? Half of 100, it will be 50 gram remaining. The second half-life comes and it will be half of 50, so it will be 25 gram remaining. And the third half-life comes and it will be half of 25, so it will be 12.5 grams remaining. This totals 3 half-lives, and the final amount which we are left with is 12.5 grams. We can also solve this problem with 3 half-lives correspond to 3 half, and that times the original amount, which is 100 grams. And when we calculate, we get the answer 12.5 grams. Let's work on one more problem. Let's calculate first how many half-lives we got. The half-life is 60 days and the total time is 360 days. So when we divide 360 by 60, 6 half-lives is the time which we have to consider. So let's find out how much of that will remain after 6 half-lives. At time 0, we begin with 12 grams and let's represent 6 half-lives which we need to get. So from 12, we go down to 6 grams. From there, we go to 3 grams and so on. Half of 1.5 is 0.75 grams. That goes down to 0.375 grams. And that final answer is 0.1875 grams. And in both the problems, we also need to find out how much of the sample actually decayed. That will be simple. We take the original amount, which is 100 grams here, and we find out how much was decaying. So that was 12.5 in the first example. When we subtract that, the answer is 87.5 grams. That will be the amount remaining. And for second problem, it will be 12 grams, and from that we subtract 0.1875 grams. And that gives us the final answer, 11.8125 grams as the amount which is actually decaying. So guess what? You guys learned how to balance nuclear reactions and also how to do calculations with half-life problems. I guess you guys enjoyed the video. I'll see you again in next video. Until then, bye-bye.